Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Our today's topic is range image processing. So let us consider what is meant by this range data or range image. It's a digitized surface data, and that's why we call it also 2.5D, because 2 dimension is usually a 2-dimensional space, and because there are surface information which will have a functional value at every point of 2-dimensional space. That functional value is itself is the height of the surface. So that's how it's a we interpret it as a 2.5D data instead of 2 dimension, or we can consider also it's a 3-dimensional representation of a scene, because you have the point sets, and if I represent the point set as a set of points, that's a kind of 3D representation. So in its form, the range image itself, as you can see, it's a 2-dimensional function, like the intensity image or optical image, which is also a function over a 2-dimensional space, which was brightness value at every point. In this case, instead of brightness value, we have the depth of the corresponding visible surface. So depth here means the distance along the z-axis. So if your xy plane is your is a plane of your discretized grid, that means every point in that grid will have the depth information, or we will have its z coordinate, and that z coordinate is what is there, it's as dij. So it can be represented as an array, like an intensity image or color image. So there is one example we are showing here. As you can see, this is the optical image, familiar optical image, and you can see the objects here. It is captured in a laboratory by placing these objects, whereas this image is a range image. It is captured by the Microsoft Kinect device, which captures both optical image and range image, and of the same scene. So here we could see that these bottle surfaces, they are shown with certain graded intensity values. Now here intensities are I should say they are proportional to the respective depth value. You can see the wall section. This is a wall, and here it is, the brightest points are at the walls because it is farthest, and the nearest closest points, all these closest points, they are darker, and the bottle surface in between, what we can see here. So just as I mentioned, it could be also in the form of a set of 3D scene points or point cloud. In that case, we will simply list it as a point. Say we will consider it's a list of 3-dimensional points, where each point is a surface point as per our understanding. So there are various imaging techniques which involve in capturing this kind of depth data or range image. So one, primarily they are categorized into two approaches. One is passive imaging, where like the camera, optical camera, you take the sensation from the environment only, take the stimulation from the environment only, and you get the image from there. So in this case, for example, stereo imaging, we have discussed earlier, that principle could be used to get the surface point. So stereo imaging is one such technique by which you can capture the respective 3-dimensional information, location of a point and you can sense the depth in that way. But there are other methods which is which falls in the category of active range sensing, because what you do, you actively project some energy or ray on the surface of the image, and then we we sense the reflection of that ray from that surface. We detect the reflections, and by detecting the reflection, we get the surface information in various ways. So, in this active range sensing, active imaging principle says that there is an additional energy that you have to project on a particular object. So, the methods which fall under this category, one is called time of flight sensors, then triangulation based sensors. Structured light is also another innovative way of applying the same principle, stereo principle here also using an active imaging technique. So, first let us consider this time of flight range sensors, the principle behind them. The principle is very simple. So, you have a illuminating source. Usually this is a laser source which which projects a laser ray to the surface, so which emits the radiation laser ray, and then it detects its reflected ray. So, the time of its emission and time of its detection, that is noted. By using the speed of that light, you can get the respective distance. So, this is called, it is a basically pulsed laser, because when you are transmitting a pulse, and when you are detecting, you will be detecting a pulse. So, the detection becomes more precise when it's in the form of a pulsed energy. Now, when we consider the other kind of active range sensing device using the triangulation based method, the same principle what we followed in the stereo imaging setup. But instead of two cameras, in this case, we have one camera and the other one also again a light source. So, which means what we are detecting here, we are detecting the reflected point. That means the light which is projected on the object surface, it gets reflected, and incident light gets reflected, and that is detected through this camera. So, this is the image point. So, the advantage here is that the point correspondence problem becomes simpler, because for this light beam, we know we have a control. We have a control over the path of projection of this ray. So, this control is known. With certain calibrations we can get this control. So, in a reference three-dimensional coordinate system, we can exactly get the respective equation of the line along which this light beam is being transmitted. So, if hypothetically, if there is any particular two-dimensional plane on which this path is considered. So, suppose this is the point through which this light beam that defines this ray projection ray, and the measurement of the distance, that is also recorded here. So, you get discrete grids of points where these light beams, light rays are defining these paths, and every time you are detecting the illuminated point, which gives you the image of that particular object point. So, you get the ray because of the same camera calibration method can give you the respective three-dimensional equation of this line using the camera geometry, and also, as I mentioned, through the calibrated projection system, you can get the equation of this line. So, this is equation 2, and the intersection of these two lines will give you the respective surface point. Now, the same principle is used in a more efficient way, where instead of projecting transmitting a single light beam from this light source, we are projecting a strip of pattern. That means strip of light source. Suppose we have we have in this light source, there is some collimator, vertical slit is there, rather vertical slit, and this light is projected only along this slit. So the advantage, once again, you have that you know the equations of these rays, because if you can calibrate this strip, then each point will be corresponds to one of these rays. So when you get a structured pattern, so this is the structured light. When this pattern is observed, so we know that this point corresponds to the reflection or the image of the object surface point, which is illuminated by this ray. Similarly, this point is illuminated by this ray, and any intermediate point accordingly can be related. So for every point, we get its respective three-dimensional ray of path of transmission of ray. So in one shot itself, we can get depth information of all the points lying over this strip. So that is the advantage. It makes your sensing very fast. Earlier, you are only computing depth at every point in one after another independently. Here, you are computing all the points on a vertical strip co-located together at the same observation. So that's why how you get the 3D positions of all the scene points lying on the projected strip. So this structured light method is made more systematic by considering certain set of patterns, allowing certain set of slits only to be projected on the surface. So there is certain kind of encoding of illumination of every surface strip. So consider, say, this is one such pattern which is being projected. Then this is another pattern. Then this is another pattern. You can see that these vertical strips can be encoded like a binary strips, where each, if there are certain discrete at the very final level, if these are the units of slits, then considering any particular position, we can say that whether it is illuminated by which. So these patterns are also indexed. So by which pattern it is illuminated, accordingly you can put a binary coding of the position. So that's how the binary codes are associated with a strip which is being projected. So just to consider, suppose this is a surface point, and consider this is a strip. Now this strip will be illuminated. Suppose if I use this one, now this strip may not be illuminated because this is the dark, this portion is the dark position, and from here the light source is being projected. So this strip is not illuminated, as you can see, this position. But when I am using this one, that means we have this and this, then again this strip is illuminated. So for this you get 0, for this pattern you get 1. Again, when I am using this slit, so each are independently, one after another, they are being projected. So there you get another subdivision, and which may happen to be also illuminated. So it becomes the coding for these three patterns, it is 0, 1, 1. So in this way, every position, every strip will have this kind of encoding. So what is required, instead of one after another illuminating the strips by the structured light projections, I can only use 3 projections using these strips, but I can identify any vertical strips using this, and at least 8 vertical strips using these 3 binary codes. So this is a advantage of this kind of space encoded structured lighting. So let me elaborate a little more. So as you can see, number of stripes get doubled at every new pattern, as we see here also. This it is 2, then it is 4, then it is 8. It could be also finer, it could be 16, like this. And each light point is associated with an m-bit binary code, and its image is observed. So this is one particular example. As you can see, this is the object, and you can see that all these projections, it just shows with animation repeated in a cyclic pattern. Only few patterns are projected. So suppose you are using 3 patterns. So only thrice we are taking the image, but we get information of every vertical strip using this space encoded pattern. So for this, say, structure vertical slit at this location, as you can see that for this pattern it is illuminated, for this one it is not, and for this one again it is illuminated. So this point, this vertical strip will be encoded by 101 with these 3 strips, and it can go on, and from there we can compute the respective 3D information. Now this further you can use a more efficient way of space encoding with very technological preciseness. If you have some kind of identify certain point, every point could be uniquely characterized by unique pattern with neighboring pattern. So if you can get that kind of mask through which the light sources are projected, but they are all colored, so the lights get colored. So these are colored filters. So suppose this is, and that shape, that means size of the dot and color of the dot varies. Say this is one such example. So you take any particular point, say this point. So you see that this is characterized by its neighbors with this kind of distributions. Wherever this point, it's uniquely characterized by another distribution. But these are all unique. So what you do in the object, image of the object also, you search for this pattern. It's like texture finding. And the point which matches with this kind of neighborhood pattern, you know that with respect to which grid of the disk. So in this grid you have these patterns, and from there the lights are projected. So you can identify once again that which light is projected, what is the equation of that line in the 3-dimensional reference plane, and observing their image once again using triangulation, you can get the respective 3-dimensional coordinate information. So this is a very innovative technique which is used in the device called Microsoft Connect, and your imaging becomes also very fast. So as you see, the pattern provides a code word associated with a calibrated light point. So it does not require multiple projections. Just with single projections you can get the range image, and it makes the system faster. So this example what I have shown earlier, this already I have shown that this is now captured by the Microsoft Connect. They provide both the color image in the RGB space and also the depth image. That's why the images, pair of these images are called RGBD images. Actually, it's a 3-channel. It's a 3-channel, and depth is another additional image here. So with this, I have just given a very brief overview of different kinds of range sensing techniques. But now let us discuss that how range images are processed or analyzed. Now, as we understand, the difference from the optical image and range image is that in the range image we obtain the digitized surface information. So it is the geometry of the surface which needs to be understood, which needs to be analyzed. That's why the geometric analysis, and in particular digital geometry, that becomes one of the fundamental mathematical tools for analyzing range image. And we need to understand then geometry of curves and surfaces. Now let us go through a little bit some fundamentals or basic concepts on differential geometry involving parametric curve and parametric surfaces. So when we say when we talk about a parametric curve, we can denote a parametric curve as a function, as you can see. So in this case, it is basically a mapping from a real point, from a real space to a 2-dimensional real space. So by a single parameter, you are basically you are denoting the 2-dimensional. It's a 2D parametric curve we are discussing. So 2-dimensional coordinates. So in 2-dimensional, we know that every point has a 2-dimensional coordinate. But when we are considering a parametric curve, so we consider at any point it can be defined as a function of a parameter xt and yt, where this is a coordinate and t is the parameter. So as we vary t from certain value, from say value between t0 to t1, these values will vary, and those coordinates, sequence of coordinates, they will define the curve. So in this case, our representation is ut and vt instead of xt and yt, as we have shown. So this is a parametric curve. So when we define a tangent at a point, as we know, in a common intuitive way, we can say that you take the derivative with respect to t, and that's what we do, that for every coordinate function or parametric function for every coordinates, you take its derivatives. So that would give the direction of the tangent. Again, you can see it's a parametric description. So in fact, if I consider a two-dimensional curve in the classical 2D coordinate representation, so a tangent, that the slope of this tangent is given by derivative of dy dx if this curve is a function of x. So when we express in this, so you can get this derivative. So which can be also here written as, say, in this case, since x is given by u and y is vt, so we say dv dt by du dt, which will give you dv by du. So that's the interpretations here. So you take the derivative and you get the respective tangent vector. Whereas the curvature at a point, it is expressed in this form, where it is a cross product of two vectors. It is basically the two-dimensional vectors, which is effectively is a determinant. So this is defined as the determinant of the first derivative vector, row vector, and then the second derivative row vector. So that is how the first row and second row is defined. And this is the first derivative, like this x prime is the same here. So you get the magnitude of this tangent vector. So I can write it also, it is magnitude, and then you take the q. So this is how this is defined. So when we consider a three-dimensional parametric curve, so in a 3D coordinate system, you have a parametric curve which every point which will have a three-dimensional coordinate point. So now instead of so every coordinate will have a parametric function. So this is how the simple extension. And when we consider also tangent, this tangent is defined as a derivative. So it is the derivative, functional derivatives for every coordinate. That is how the tangent vector. So if I consider a tangent vector, and this is again definition of a parametric curve. So at this point, if I derive all these coordinates function with respect to t, then we will get the tangent derivatives, tangent directions. And curvature, following the same expressions, we have the determinant of the cross product of these two vectors. Now, since these are all three vectors, we know how to compute the cross product using that determinant rule. And this is once again the tangent, the magnitude of that tangent, and q of the magnitude of the tangent. So this is how it is computed. So this is as I mentioned, this one is defined as cross product of three vectors. So note the difference. When we have used in 2 dimension, this was determinant of the first derivative and second derivatives row vectors. But when we use in 3 dimension, then it is the cross product of first derivative and the second derivative in the same way, but there you can express in the vectorial form, and you can get the corresponding magnitude. Now there are certain interesting fact that some of the other entities that could be defined when you are considering a parametric curve in 3D. Because when we consider a parametric curve in a 3D, then how do you define the normal of the curve? In 2D, the normal is well defined, So if you have a curve in a two-dimensional coordinate system, then we know that if you consider a tangent, then the perpendicular to that tangent will give you normal. In fact, the curvature that at that point, the reciprocal of that curvature will give you the radius of the radius of the circle, which will be just touching this tangent. So that is also called radius of curvature. That reciprocal will give you the radius of curvature. So in three dimension, now since we have to consider certain plane on which this curve is lying, but as it's a three dimensional curve, this could be folded. So it is not a planar curve, but in a very I should say, in the limiting case, we may consider a very small, it's a tangent and there is a very small, very neighborhood point. So one tangent and one, point that defines a plane itself. And if I consider that plane, so this plane will be, defining the plane where this kind of normal to that tangent will lie, and the respective definition of radius of curvature will be valid in that case. So we call this plane as an osculating plane. So let me show it in a more cleaner way. So this is the definition of an osculating plane, and then this is the normal at that point. So we say this is the curve, and this is a tangent. So this one is the tangent, and this is the point. This is the point. So again, this normal and this tangent, this plane. So if I consider a normal which is normal to both this tangent and this normal, if I consider another direction which is perpendicular to both, this is the normal, say n, and this is tangent t, and say this is b. So they also define a plane. So this n and b will define another plane which is called normal plane, and this direction is called bitangent. So this is the osculating plane. This is normal plane. This is normal has been shown by this notation, and this is a circle, as I was mentioning, this radius of curvature with respect to the center of the circle, and this is normal plane. And this plane which contains this bitangent and tangent, it is called rectifying plane. Okay, so sorry, this is called binormal, not bitangent. This is called binormal. So this binormal and tangent, they form the rectifying plane. So now you see that at this point you are having a three-dimensional coordinate system whose principal coordinate axes are defined by tangent, the normal and binormal at that point. So, and at every point you can have its own three-dimensional coordinate system. So this is this kind of interpretations, so this kind of representation is called Freinet frame or moving trihedron. So at every point you can define its own coordinate system with respect to this geometric structure. And some of the relationships between these three entities, tangent, normal and binormal. So the derivative of tangent, so if I consider the derivative of the tangent along these directions, now that would give you the curvature. You see, this is the curvature along the normal. Actually, the definitions, when I said in the two-dimensional that the derivative of the slope of the angle found by the tangent with respect to the length d psi ds, you see that relationship is reflected here, because that is the quantity which is the curvature, and there is a vector associated with it, which was not very much understood in that case. But now it is, if I take the derivative analytically for this parametric curve, we get the direction of normal from this derivative itself, and its magnitude is the curvature. You note that these are all unit vectors. So you take the derivative of the unit vectors, and then you get the respective value, which again is expressed in terms of magnitude and unit vector. Right. Then the other relationships with respect to binormal and normal is also there. That means derivative of binormal is associated with once again in the direction of normal, even the derivative of this one itself in the same direction, but this is the parameter which is called torsion. And on the other hand, derivative of normal, it is a linear combination of these two vectors, tangent and binormal, and it takes a linear combination of both curvature and torsion. So it's a very interesting relationships which are used in various geometric analysis. Let me discuss about parametric surfaces. So we discussed that for a parametric curve, we require only one parameter, whereas for a surface, we use two parameters to represent a surface, because we know that a surface topologically is a two-dimensional entity. And when we are considering representation of this surface in a three-dimensional coordinate system, then we can express the coordinate points all lying on the surface once again by as a function of two parameters. So the parameters which varies continuously within certain range, they define that set of points, those set of points lying on the surface, or they define the surface. So it's a representation in the continuous domain, and we can consider that the respective mapping would be from a two-dimensional parametric space to the three-dimensional coordinate space. So this can be appropriately represented, as you can see that a point in the three dimension which is lying on the surface, their coordinates are represented by these three functions. Earlier we have seen that again in three dimension how a parametric curve also can be represented as a for whose coordinates are represented as a function of single parameter. And we are considering now these two parameters, we are denoting them by the names u and v. So at that point. Now if I consider a particular point in the surface, suppose this is a point and there is a specific value of u and v, say consider the value is u naught and v naught, and as we know that for this surface representations we can since it's continuous, we can consider that there is a tangential plane touching at this point, and this tangential plane, it has its normal, which is called normal of the surface. Now for the parametric description, what we can see that at this point, suppose you have a curve which is varying with u, but v is constant, say v equal to v naught, at this point u naught, v equal to v naught, but with this small interval we can say very small interval, there is a smooth curve passing which is varying between say some interval, say u1 to u2, where u naught is within that point. So if I take the derivative along u, or the partial derivative along u, that would give me the tangent tangential directions which is lying on that plane, the direction of the tangent which is lying on that tangential plane. Similarly, there could be another say curve which is lying on the surface where u is kept constant and v is varying. So v is varying. So once again the tangent at that point can be obtained by the partial derivative with respect to v, and we know that a normal of the plane is perpendicular to those tangents of the tangent plane. So if I take the cross product of these two vectors, then we will get a normal. So that is how we are getting say xu, it is representing actually the parametric representation of the partial derivative of this surface xuv. Similarly, so it's a three-dimensional vector, as you know, it gives a three-dimensional direction because it can be considered as delta x, delta u, delta y, delta u, delta z, delta u at u equal to u naught and v equal to v naught. So this is what delta x, delta u, or partial derivative of with respect to u. Similarly, you have the partial derivative with respect to v. So these are the two tangential directions as I have shown. This is delta x, delta v, and this is delta x, delta u. So if I take the cross product, I will get the direction of the normal, and I can normalize this vector by the magnitude of that vector, of the respective vector. So that is how you get the surface normal at any point of this parametric surface. So this is exactly, that's what I discussed. You can consider these are the two tangential directions and this is the tangential plane, and you get the normal. So now let us consider another interesting thing by which actually we would like to analyze the local geometry at a point on a surface, and that is the curves passing through that point which has a parametric description. So any parameterized curve on the surface, that could be again represented very simply when I make u as a function of the parameter t and say v as a function of parameter t, another function, it is not the same function, of parameter t. So overall then I can write all the points which are lying on this curve, I can express them in terms of say xt, or I can write ft gt. This is the point uv equal to x ft gt and henceforth. So you can, as you can understand now, so this can be equivalently considered, that's a function of only single parameter t, which is a once again which gives us a three-dimensional curve, description of a three-dimensional curve, and at certain point u naught and v naught, this curve. So whichever point is lying on this curve, you can use that property of that curve to extend those geometric properties of this curve to those points, and it becomes helpful in our representation. So that as I was mentioning, that let us consider once again that u and v as a function of t, which I am expressing in this form ut vt following the similar notation. So finally a parametric curve lying on that surface is given by these coordinates. So this is the coordinates x and this is the coordinates y and z. So tangent vector to this curve, that is interesting, that we can compute, as we know that beta prime t should be the tangent, but when you are doing derivative, partial derivative with respect to t or with respect to derivative, so what you have to do, you have to derive again, first say derive x, derive delta x, delta u, and then perform delta u, delta t. So I can write in this way, simply I will consider that this is u prime t x u, and because delta u delta t is common, so which means this part is giving me delta u delta t, and then I am writing delta x delta u and delta y delta u and delta z delta u as a vector. So you are just simply multiplying it. So this is a vector, so you are doing it in every dimension, this part. Similarly for the v also you are doing the same things. Now there are two particular entities which we would like to measure for this curve. As I say that if I have a parametric surface and suppose at a point there is a curve. So at this point I would like to measure the magnitude of the tangent. So how do you express? So for any arbitrary curve at this point. Now we can show that this could be expressed by two factors. One factor is determined by the respective intrinsic geometric properties depending upon the functional variations of u and v parameter only. Whereas, so that is not dependent on this parametric curves variation of the parameter. So for any curve passing through that point, it will have those entities. But the special thing would be also required for this curve, where actually the variation with respect to the parameter with respect to the derivation of u and v with respect to the parameter t needs to be considered. So this is captured by a form which will give you ultimately the measure of the magnitude of the tangent, which is called first fundamental form, and this is how it is expressed, that if I consider any two vectors u and v, it is not parameters, note that these are two vectors, it is a overused notation in this case, it is just the dot product of two vectors. Now if I take it along the tangent at that point, as you can understand, it will give me the magnitude of the tangent. So with respect to a curve beta t, we can define this first fundamental form. As I was mentioning, that I am interested on the tangents, how this quantity is computed. As you can see that this is the tangential vector, and if I take the dot product of these two tangential vector, then finally the reduction doing the algebraic manipulation, we can express them in this form. So this is these are the partial derivatives with respect to u and v. So you can see that this is a dot product of x partial derivative of with respect to u, then with respect to u and v, and so this is defined as E, F, G. These are quite well established notations which are used usually to express this kind of form. So these quantities, these first derivatives are with respect to parameter. So if I consider any arbitrary curve passing through that point, all these values E, F, these coefficients E, F, G, they remains a constant. Only you need to measure the variations of those parameter of u and v with respect to t, value t, and so the value of t at that point will give you directly this first fundamental form. That is the advantage you have. So the definition of E and F is once again given, and these three coefficients gives you the helps you in computing this first fundamental form efficiently. So it is basically measuring the magnitude of the tangent vector. The other quantity which would be related to the curvature at that point. So if I consider the normal section, that means if I consider the normal and this tangent, and if I take the plane, so at this point, now this curve, this segment of the curve will lie in this plane, and we call this kind of the curvature of that particular curve at this point, we call it as a normal section, or the curvature, normal curvature at that point. So we would like to measure this kind of curvature. So the second fundamental form is relating that. So what it is doing, it is measuring the dot product of the vector u and the derivative of the normal vector, so differential normal vector, I should say differential along the V, which means dot product of U, and this is the NV, and we can show that this is related to the curvature at that point, because the tangent and normal, they are orthogonal. So by using this relationship that their dot product is 0, we can express that the relationship between this tangent and this particular entity, that variation with respect to the V, that means this vector, the variation with respect to V. So that is related. So how the tangent is varying with V with dot product of n and also this t, and this can be, as we have seen earlier for the parametric curve, the gradient of tangent along the parameter, that can be expressed in terms of the curvature and the normal of that curve. So that is how the curvature is coming into picture. So this quantity is equal to, if I compute second fundamental form again at the tangents, this can be written as this curvature and dot product of these two. These are all unit vector. So the normal of the curve and normal of the surface, the angle they make, and this is cos phi, and it can be, if it is a normal section, actually this would be in the same the angle between this would be 0, and we can show that this is equal to the curvature at that normal section kt. So when we measure in terms of, this is called normal curvature, as I mentioned. So when we measure, when we express these things using the respective differential geometric quantity, that means all those derivatives, the second fundamental form can be simplified into this form. Once again, almost similar structure. So these are the quantities, coefficients, which are related to the variation of parameter u and v only over the surface. So this is not specific to that curve, whereas for specific to that curve are these two quantities, are these three quantities. So these coefficients are the coefficients of the second normal form, and they are defined in this form. They are the dot product of the normal, surface normal, and the second double partial derivatives of those coordinates. Normal curvature, this is expressed as the second fundamental form normalized by the magnitude of the tangent. So the expression of kt can be also given as a ratio of these two quantities. So this is also another relationship. Now there is one particular quantity related to these coefficients, which is which characterizes the surface. So I am just giving you the result here. So this is that quantity which is called linear map. As you can see that coefficients of both the first fundamental form and second fundamental form, they are used. So it is basically you can see that this is the this is related to the second fundamental form, and this matrix is related to the first fundamental form. And taking the inverse, the properties of linear map is that actually it is related to the curvature very directly. So if I take the eigenvalues and eigenvectors of the linear map, the eigenvectors, they give me the directions of principal curvatures, and eigenvalues are those curvature values. Actually, let me explain that if you have a point in a surface, as I mentioned that there are infinite number of curves which can passes through this point and which are lying on that surface. Now each curve will have its own curvature. Each curve has its own curvature because of this curvedness, okay. So they have their own curvature. Now there is a direction, so that this tangent at that curve provides that direction of that curve, that is related to that direction of that curvature. So there is a direction where this curvature value is maximum among all those curvatures, I should say magnitude of the curvature, and there is another direction which would be minimum. Incidentally, there it can be shown they are orthogonal. So those two directions are called the directions of the principal. Those two curvatures are called principal curvatures, and those are the principal directions. So those can be obtained from the linear map, which are again associated with the coefficients of the first fundamental form and second fundamental form. So it is totally a property of the surface. You see that the parametric variation related to a specific curve is not considered here. And there are either expressed in terms of principal curvatures, or there are two other quantities which are also functions of principal curvatures. I am not going to discuss much on their interpretations, but let us know them. One of them is Gaussian curvature, which is actually product of these two principal curvatures, and this can be measured as a determinant of the linear map. And the mean curvature, which is the mean of those curvature, that means half of the summation of those principal curvatures, and it is also half of trace of linear map. Those are measured, and those things are related, since this linear map we can perform this determinant and these things. So these are the expressions, and this is how those coefficients of first fundamental form and second fundamental forms are used for computing these curvatures. As you can see, actually H and K, they nicely, this capital H, capital K, using them you can define a algebraic equations, and using the theory of quadratic equation, you can consider that the solutions, if the solutions is K1 and K2, as you know that K determines, this capital K determines the product of that solution, and whereas minus 2H should be the sum of this one, whereas H means K1 plus K2 by 2. So this is also consistent with respect to this. So finally, by solving this equation also we can get principal curvatures in terms of Gaussian and mean curvatures. So the use of curvature in understanding the geometry or topology of surface, local geometry of a surface or local topology of a surface is very I think that is very useful. That is what these curvatures can be used for characterizing the local topology, because to give you the idea intuitively, see, if I consider a curve in 2 dimension itself, so suppose I have a coordinate value, say this is x and y, and we know that a curve is a function of x, say fx, which is basically in y axis we are putting fx. Now when we are considering a kind of shape, so this shape, suppose this shape is a shape which we are saying is a shape of a peak, okay. So it's a kind of, say, convex shape in this case, or the shape of a peak. So if we can see that in this case, when you are changing the angles, now these angles are basically decreasing. The value of this angle, as you go on, it is decreasing. It is going to 0 and then to the other directions, negative, with respect to, say, x-axis. So which means that as I defined curvature also, the derivative of this angle of these tangents with respect to the length, with respect to this over this curve's length. So which means this curvature is negative. This curvature is. Similarly, if I consider the other way, that's why you see that for finding out maximum double derivative, see, curvature is also double derivative, it has to be negative. On the other hand, when the shape is like this, there the curvature would be positive. So if I consider now a 2-dimensional surface, now you see that this is your plane. So the curvatures, principal curvatures, if I take the product of these principal curvatures, or the two principal curvatures, if both of them are negative, then it's a shape which is like a peak. On the other hand, if I take a surface where both of them are positive, then it's like a pit. and for a flat surface, both of them would be 0. So using the sign of this curvature, we can determine various kinds of topology of the surfaces. So with this, let me just give you some of those results. As you can see that peak is h is greater than 0. I am showing with respect to mean curvature and Gaussian curvature. Here actually I have said K1 and K2 both are negative. I will just show one example, then others will be understood. So the product of K1, K2, since both are negative, that would be positive, whereas mean of K1, K2, since both are negative, it would be less than 0. In the pit, again, both are of the same sign, but they are positive. So it is greater than 0. Both are positive, so it is also greater than 0. For flat, I have already mentioned both are 0. So the product would be 0, mean would be 0. And a combination of this, that means at some side it is flat and also at the other dimension it is convex, or it is basically forming a peak. So you have this. Since one of them is 0, product would be 0. But the other one would be negative. The sum would be negative. Similarly, the valley. Once again, this is the other surface. So there are such surfaces, and using them, as you can understand, if I give you a parametric surface, by computing their curvatures, you can find out the local, you can predict what should, or you can analyze what should be its local topology. Now, when you are considering a range image, since range image, it's a discretized grid, and at regular point intervals, you are getting the depth information. So it can be considered as a digitized version of a surface. That means every point gives me x coordinate, y coordinate, and the z coordinate, which means the parametric description, it is a function of u. So if I write x u v, that should be equal to u, whereas y u v, this should be equal to v, and z u v is the respective range function, range value, which is shown here as h u v. That is how a point is characterized, and this is shown here. So with this representation, if I apply the same analysis, I can see that how this first fundamental, this kind of coefficients, they are expressed with this analytically. As you can see that this is a surface normal, and this is the directions, and this is E, F and G, this is small e, small f, small g. So these are the expressions, and it comes directly from the expressions which we showed. So by using this, if I give you a discrete discrete function like range image in the digital space, you can estimate those values, and locally you can get the characteristics of the surface, and by accumulating them, there are algorithms by which you can segment range images. So with this, let me conclude my talk on range imaging. So as we discussed that there are different types of range sensors, and you can use different kinds of technique. So stereo imaging is one such technique, which is the passive imaging technique, but there are active imaging technique where you can use time of flight based technique, triangulation through scanning beams, structured lights based technique. Those things you can do, or you can project some patterns, and from the patterns uniquely define the neighborhood and also the projected ray and get the depth information. Then we also discussed use of differential geometry in extracting the local features of a pixel. In a range image particularly, we have shown that how curvatures could be estimated and how their local, how it could be interpreted, used for interpreting the local topology. So these are the certain things we can compute: surface normal, principal curvatures, Gaussian curvature, mean curvature, and using signs of curvature, we can characterize the local topology of surface. So with this, let me stop here. Thank you very much for your patience and listening.